Hello students, welcome to EPG Pathshala. I am Dr. Ajit Kumar Mahapatra from the Department of Physics and Astrophysics, University of Delhi, Delhi, India. Today we are going to discuss about the module Low Voltage Surface Electron Microscopy coming under the topic Surface Morphology from the paper Characterization of Materials Part 2. From this module, students may get to know about the following: the changes in beam surface interaction for low voltage scanning electron microscopy, and the advantages and limitations of this low voltage SEM. Then we will go to discuss about the contrast formation in LVSEM. In scanning electron microscopy, as the beam voltage V0 is reduced in the range of 1 to 30 kilovolt, three physical parameters relevant to specimen damage, surface charging and topographic contrast also change. The secondary electron coefficient delta increases to unity. The electron range R is equal to k V0 to the power 0.5 and the energy deposited per electron EV0 both decreases. When delta is large, there is less surface charging on the insulating surfaces and there is more signal per beam electron. A smaller electron range means the beam specimen interaction is more localized and the image contrast is higher. The possible technical limitations can be grouped in four categories. First one is low source brightness, second increased effect of chromatic aberration, third increased sensitivity to stray fields, and four is the deep focusing of the probe by the secondary electron collected field. As the beam voltage is reduced to a value where secondary emission coefficient is equal to or greater than unity, the surface potential gets stabilized. These conditions are independent of the angle of incidence of the primary beam and the collector is controlling the image contrast. The image contrast is resulting from the changes in the secondary electron coefficient from different elements, and this effect would be largest when the secondary electrons yield is maximum, that is at low beam energies. The choice of electron energy range. The interaction between the electrons and the material is much stronger in the energy range of 100 electron volt to few kilo electron volt than at higher energies. The consequence of this stronger interaction is that the penetrating depth of the electron falls rapidly as the incident energy is reduced. The penetration depth is measured using Bethe range RB, which is equal to integration of E minimum to E0 minus 1 by dE by ds dE. The low voltage image is more sensitive to the chemical nature and topographic form of the specimen surface. In the low voltage SEM, since all the signals are produced near the surface of the materials, even very thin specimens could be as bulk. The relationship between the secondary electrons and backscattered electrons BSE images could be reversed under low voltage operation. The contrast information of the secondary electron image for typical SEM energies of 20 to 30 kilo electron volt generates from a depth of about 4 lambda from the surface, that is about 15 to 20 nanometer. However, the average backscattered electron emerges from a depth of about 0.2 Rb, which is approximately 0.25 micrometer or more. The backscattered electrons carry the information and the secondary electron carries the surface information of the material. At low voltages, the energy distribution of the secondary electron does not change with the incident beam energy, leading to the identical depth of information for the secondary electrons, that is 15 to 20 nanometer. However, the depth for backscattered signal, which is 0.2 Rb, reduces to 3 to 5 nanometer due to the fall in electron range. Hence, secondary electrons are emitted from the whole of the interaction volume at low energies, while the backscattered electrons emerge from the near top of the specimen surface. Thus, at low voltages, the secondary electrons perform the task of bulk imaging. The schematic diagram of the beam sample interaction in a large number of SEM is plotted in the figure. At low voltages, the SE1 and SE2 components provide high resolution information, and the SE3 and SE4 components are noise that degrades the signal to noise ratio. Let us see what are the advantages of low voltage SEM. In low voltage SEM, where V is equivalent to around 1 kilovolt, the electrons used for impinging the specimen's surface with low energy penetrate a shorter distance through the surface, possessing a larger cross section and produce secondary electrons near the surface where they can escape. As the signal to beam electron ratio increases, that is, the secondary electron coefficient approaches to unity, the charging effect also diminishes due to the decrease in amount of energy deposited on the surface. This proves to be a great advantage for non-conducting photoresist and passivation layer. Another advantage is the result of reduction in beam penetration results, preventing trapping of charges that might distort the energy band structure of the sample and degrades its functional properties. At around 1 kilovolt, such degradation is restricted to the outer surface of 0.02 micrometer and goes to 130 times deeper at 30 kilovolt, making a significant difference in samples of few micrometer dimension. As discussed, the changes in the electron-solid interaction with the incident beam energy affects the contrast formation in the SEM images. The most significant effects are the reduction and eventual loss of contrast from topographic image and beam penetration. The beam penetration into the sample contributes on the SEM image contrast. At high beam energies, this occurs over a scale of many micrometers and features raised above the general surrounding surfaces are exposed by the incident beam irradiation, leading to enhanced secondary electron emission from all the free surfaces of the feature. The 20 to 30 kilo electron volt micrograph shows all the expected features of a typical secondary electron image, contrasting from the topography of the sample surface, edge brightness enhancing the shape of features, and a three-dimensional appearance that makes easy interpretation of the image. As the primary beam voltage is reduced, the beam penetration becomes smaller than the typical dimension of the sample's feature. The resulting image flattens and provides a two-dimensional appearance, which can be explained as the replacement of the earlier image contrast by a simpler directional shading, where one side of the feature is always brighter than the other side. Thus, analyzing the low voltage 1 kiloelectron volt SEM micrograph in comparison with the high voltage SEM images would not be appropriate. It is also evident that the surface contamination marks, scratches, and dust particles, which are barely visible at 10 kiloelectron volt, became dominant for contrast formation in 1 kiloelectron volt image due to a significant change in the form of the image contrast associated with a subsequent rise in the secondary electron yield due to fall in the electron range. At high energies, most of the secondary electrons generated within the interaction volume are far deep inside the surface to escape and do not contribute to the observed signal. The efficiency with which the secondary electron detector collects the secondary electrons from the materials also contributes to SEM image contrast. At high beam energies, more secondary electrons are emitted so that the beam penetration contrast, the topographic contrast, and the detector efficiency contrast all contribute to the SEM image, and face tilted towards the detector is bright because these collected most of the secondary electrons. Also, the face tilted away from the detector emits more secondary electron than at normal incidence, but a smaller fractions are collected by the detector. Here, the topographic contrast is moduled by the detector contrast effects to produce the characteristic shading that makes surface and topographic readily interpretable. The features of the sample comparable to or smaller than the beam range are filled by the interaction volume produced enhanced secondary electron emission that contribute to the three-dimensional appearance. At low voltages, the beam penetration is small. All faces of the sample emit about the same number of secondary electrons. The features raised on the surface no longer display enhanced secondary electron emission, leaving only the detector contrast contribution to measure. The results, the SEM image appears flatter, less dramatic, and the true nature of the specimen surface is hard to discern. The electron yield is defined as the total number of electrons exiting a material divided by the number of incident primary electrons. The electron yield varies as a function of accelerating voltage as shown in the figure. Electron yield gives a value of unity twice for this plot, and these points are termed as crossover voltage. The lower crossover voltage is designated as E1 and the higher crossover voltage is E2. E1 is too small to be measured with existing low voltage SEM technology. However, E2 ranges from 500 electron volt to 3.5 kilo electron volt for most insulators. The part of the curve between E1 and E2 defines the range of voltage where positive charging occurs, in which the number of electrons exiting the sample are more than the electrons entering, resulting in a net charge depletion at the surface. Positive charging results as a darkened region in the sample while imaging, as the net positive field locally holds back the electron yield. The part of the curve for voltage values greater than E2 and electron yield less than 1.0 is known as the negative charge region, in which the number of electrons exiting the sample is less than the electrons entering. The negative charges build up within the coated specimen, which behaves as an insulator and displays edge bright region in the image. Negative charging can produce fields large enough to deflect the incident electron beam away from this sample or even back of the microscope column, thus prevent charging on the surface of the sample. An acceleration voltage equal to E2 should be used. The topographic contrast arises when there are local differences in the secondary electron coefficient, or if local differences in the efficiency at which the secondary electrons are collected. The local differences in the secondary electron coefficient arise when there is an edge or a local tilting of the sample surface with respect to the primary beam direction. As it happens in surface roughness, at an edge the secondary electrons can escape from the top surface as well as the side surface, as shown in figure 4. As a greater percentage of the interaction volume is within the secondary electron escape depth, tilting also increases the secondary electron yield by moving the interaction volume closer to the surface. The secondary electron coefficient is increased with tilt, as shown by the equation delta is a function of theta is equal to delta 0 sec theta, where delta is the secondary electron coefficient at a normal angle of incidence and theta is the tilt angle. Tilting, therefore, an effective way of reducing charging in polymer samples examined by shifting the crossover to higher voltages, that is, at a voltage greater than E2. In materials at low accelerating voltage, the electron range is approximately the same distance as the secondary electron escape depth. For example, in gold at 1 kiloelectron volt, the electron range and the secondary electron escape depth are approximately 50 angstrom. The result is a loss of urge contrast because the electron range is within secondary electron escape depth at every place on the sample. Therefore, tilting neither changes the secondary electron coefficient nor the image contrast. A schematic of this effect is shown in figure 4b. In polymers, however, topographic contrast is present and even enhanced at low kiloelectron volt operation. Even at low accelerating voltages, the interaction volume in a polymer is always much larger than the 200 angstrom secondary electron escaped depth. Therefore, topographic contrast has the same origins as at high voltage. At low voltages, the topographic contrast is enhanced because the total interaction volume is smaller and closer to the surface. A schematic of this effect is shown in figure 4c. The limitations in low voltage SEM. First, the brightness of thermionic sources at low voltage. The source brightness is a practical limit on the performance of SEM with a heated tungsten. The effect of spherical or chromatic aberration on spot size can be minimized by reducing the acceptance angle of the final lens A until the lens becomes diffraction limited. An instrument with conventional tungsten sources, the image becomes too noisy for convenient use and is reduced to the diffraction limit. The brightness B of a thermonic electron emission source is given by the Langmuir equation for small a, which is written as B is equal to J0 11,600 divided by pi t times V0 in amperes per centimeter square, where J0 is the current density at the surface of the source in amperes per centimeter square, T is the source temperature in Kelvin, and V0 is the beam voltage in volts. From equation 1, the low voltage V0 operation produces reduced brightness, but in practice, the brightness actually obtained is even lower than the value estimated from equation 1, because this equation is only valid in absence of space charges near the cathode surface. Such space charge shields the cathode from the accelerating field and further reduces the brightness B. For a specific gun geometry, the virtual free of space charge affects highest operating voltage, that is around 20 to 30 kilovolt. The field present at the filament surface is proportionately less at 1 kilovolt, and the gun brightness is limited by the space charge unless the geometry is changed. The practical measures to improve thermionic gun brightness at low voltages therefore includes the use of LaB6 cathodes and changing the gun geometry. The LaB6 cathodes have a comparably more pointed tip that reduces the space charge effect and are about 6 to 10 times brighter than the tungsten source for comparable lifetime. They also operate at a lower temperatures than normal tungsten temperature. T is equal to 1500 K to 2500 K. Changing the gun geometry involves either reducing the gap between the wavelength and the anode using an anode spacer, or a mechanism to actually move the anode towards the cathode, or addition of more anodes to the gun. A double anode approach and installed extraction anodes of various shapes and spacings between wavelength and normal anode are generally used. At low beam voltage V0, this electrode runs a few kilovolt above the ground to produce higher constant voltage V1 and reduces the effects of space charge. At 1 kilovolt and 2 kilovolt, this setup produces 10 times higher brighter than the typical 30 kilovolt electron gun with tungsten, and 8 times higher brightness with LAB6 using geometry depicted in figure 5. The second type of limitations to the low voltage SEM is the brightness of field emission sources at low voltage. The field emission sources have been known to produce high brightness but are commercially limited due to the following reasons. First, the requirement of 10 to the power minus 8 Pascal or 10 to the power minus 10 torr vacuum in the range around the emitter tip. Second, the current generated by the source is subjected to temporal instability that produces streaky images. Most field emission sources utilize a double anode design with V1 in the range 3 to 7 kilovolt, and it is used to adjust the beam current. A second supply between the ground and the cathode adjusts the primary beam voltage V0 to the desired level and reduces it for low voltage SEM, producing an electrostatic lens. In principle, the geometric parameters can be adjusted for an efficient emission from the tip with V1 is equal to 1 kilovolt. However, in practice, tips with sufficiently small tip radius R0, usually unstable and subject to catastrophic failure, while a suitable choice of the spacing and shape of the two anodes can reduce the lens effect to a low level. Here, the brightness of the source depends only on V1 until the lens effect degrades the source image and is given by B is equal to a V1 cube divided by phi R0 square exponential minus b r0 5 to the power 3 by 2 divided by v1, where a is equal to 8.7 into 10 to the power minus 8 and b is equal to 2.1 into 10 to the power 8, and a and b are constants. Several field emission guns have been designed to incorporate a magnetic lens that operates on the beam leaving the tip. These magnetic lenses possess advanced electron optical characteristics to the electrostatic lenses and produce improved performance when operating at high current and low beam voltage. The third limitation is the chromatic aberration in low voltage SEM. The dominant lens defect in the low voltage SEM is a chromatic aberration in the diameter of the disk of confusion due to its defect. DC, that is formulated as DC is equal to Cc alpha delta V by V0, where Cc is the chromatic aberration coefficient and delta V is the energy spread of the beam. Here, the issue arises as delta V divided by V0 increases rapidly at low voltage V0. That can be resolved by lowering Cc alpha or delta V. Lenses can be designed to reduce Cc by shortening their focal length. It is practically difficult to design a system for Cc less than 0.2 millimeter. However, it is relatively easy in terms of the total magnetic flux required to construct a lens of short focal length at low energy. Let us discuss about the issues with signal collection in low voltage SEM. The most SEMs, the secondary electrons produced by collision between the beam electrons and the sample, are collected by a field imposed at about 300 volt to attract electrons at the entrance of the scintillator or photomultiplier signal amplifier. The collection of secondary electrons using this procedure works well when the sample is 5 to 10 millimeter below the objective lens pole piece. As the working distance is reduced to diminish the chromatic aberration, the same field at the sample surface becomes less efficient for collecting signal electrons, as this field becomes relatively large compared to the beam energy, producing disturbances from the beam. To overcome this drawback, following measures are used. The first method is using an objective lens with a sharp conical lower pole piece that allows the collected field to penetrate the electron optical axis easily. This approach also permits observation of highly tilted, large and flat samples. It has the disadvantage that conical lenses often have reduced electron optical properties. The second method is to collect the signals with use of systems employed in the transmission electron microscopy or scanning electron microscopy, where initially the sample is immersed in the lens field with the low energy electrons spiral up the field lines through the hole in the upper pole piece and are finally collected by a small transverse electric field. The advantage of the system include it could work with very short focal length lenses. The area of transverse field can be carefully controlled and protected from inhomogeneities produced by irregularities in specimen topography. It is immune to variations in collection efficiency caused differences in specimen's surface potential. Also, there exist few disadvantages of this method, including magnetic samples cannot be viewed due to lack of directional collection field at the sample, and the shadowing effect is absent. The third method involves using a pair of scintillator or photomultiplier detectors, one on either side of the sample specimen, which helps shielding the axis from the field. An axial metal tube protects the beam from the effects of the collection field until the time it does not reaches the sample. So, students, let us summarize what we have learned in this module. In low volt SEM, the image contrast results due to the changes in the secondary electron coefficient from different elements, and this effect is largest when the secondary electron yield is maximum, that is at low beam energies. At low energies, charging effects diminishes and the trapping of charges reduces and results protecting the sample from any spectral disk. To improve the brightness at low energies, different gun geometry and use of LFB6 cathodes are the primary steps taken. Using pairs of scintillator or photomultiplier detectors and objective lenses with a sharp conical lower pole piece are few methods taken into account to overcome the drawback of signal collection in low voltage SEM. Thank you.